So welcome to the review session for Module 5. The same format. I have, this time I've chosen 4 types of problems for you. And I will show you the problem, explain to you the problem, and then with a little bit of delay, I'll walk through the solutions. Here is the first problem. The first problem is about a pharmacy. And the way that the prescription process works is you have a doctor, and the doctor is prescribing prescriptions, and those get filled by the pharmacist. And the pharmacist has a quality assurance person working with him or her, and that person catches a good number of any potential problems, and then the medication ends up with the patient. Now the problem, though, as you can see in the question, the problem is that the doctor makes a certain percentage of errors, 2%, and the pharmacist makes some errors, though most of them actually get caught by the QA person, the quality assurance person, and so basically they get fixed, and you can think of that as a rework loop. And then finally, even the patient is able to recognize some of the defects. And so the question here is, first, what is the likelihood that the patient is presented with the wrong medication? And then finally, what is the question what's the likelihood that the patient ends up actually taking a medication that is not right for him or her? Take some time, put me on pause, and then give it a shot yourself, and then look at my solution. All right, the way that you want to think about this is it's really probability theory, and it starts, I think it's helpful to just start with the doctor here. So the doctor basically can make a mistake, which happens with a 2% probability, or make things correctly, which happens with a 98% probability. Now, if the doctor makes a mistake, really the pharmacist doesn't really matter, and it's a 50-50 shot between the adverse outcome that the patient gets the wrong medication, and the outcome that basically the problem is fixed by the patient. Now, for the 98% cases that the doctor makes the right decision, it's left to the pharmacist now to mess up, if you wish. So in 99% of the cases, things will look good, right? So the pharmacist will do the right thing. And in only 1% of the cases will the pharmacist make a mistake, a defect. Now, if you look at those defects then, in 97% of the cases, this defect is going to be fixed by the pharmacy's QA person. And in 3% of the cases, it will be presented to the patient. And then, the patient is not particularly good at kind of recognizing. They just see the script and the bottle with the pills. So if they're the wrong pills in the bottle, the patient can't tell. And so only 10% then of the patients are able to catch this as the patient. So this is catch by patient. And then 90% here are leading to the negative and undesirable outcome. So let's look at the question and kind of, once you have this logic, and you really see the Swiss cheese argument here, that in order for the medication, especially in the right branch here, to end up in the body of the patient, there are lots of things that have to go wrong, right? The pharmacist has to make a mistake, the inspection people has to miss it, and the patient has to miss it. And so it's really a big probability term. If you look at the first question is looking at the patient being presented with the wrong medication. So we're looking at this node here in the tree. So with a 2% probability, well, the doctor makes a mistake, and that leads to the wrong medication getting to the patient. And then, we're looking at this case, independent of whether the patient catches it or not, with a probability of 0.98 times 0.01, the probability of the pharmacist making a mistake, times 0.03, the probability that the QA person doesn't catch it. We're going to get a total probability that corresponds to 2.0294%. And then in the second question, we really are interested in this kind of this final outcome here at the bottom. So those 2% here, those 0.02, we're only interested in half of those cases because the other half is caught by the patient, plus 0.98 times this same as above, 0.01 times 0.03 times now 0.9, which is a probability that the patient doesn't catch the mistake. And that gives us a total probability of 0.010265. Sorry, I had to look at the computer for this. This is a little bit more than what I can do in my head. But that gives you the answer to the questions. Now, in the previous problem, you just had to compute the defect probabilities, basically at the end of the process. Now, in this question here, we're going to look at how this impacts the capacity calculations. And so specifically, you are looking here at a process that consists out of 4 steps. Step 1, step 2, step 3, and step 4. And these 4 steps have quality problems. In particular, the second step here has a defect probability of 50%. 50% of the units here are going to go to scrap. And then the next step has a rework loop, has a 30% probability that you're going to have to rework the unit. And then you're going to sell it over here. Again, as usual, take some time, and I'll be with you in just a moment to give you the answers. All right, so the first question here looks at how many times basically does a flow unit that is served here as demand, how often does it have to be handled at each of the resources? And so the way to think about this is really, well, for the last step here, step number 4, every unit of demand has to be processed, and so that gives us a demand here of D. For the previous step, station number 3, we have 1.3 Ds, right? Because there's a 30% rework loop here. And please note that the assumption is that rework always works. So you don't have to think about a rework of a rework of a rework. So that means really every unit has to go through there, and then 30% of the units have to go through there twice. Now, as you then go into step 2, you have to adjust for the scrap. And there's a 50% yield loss. That means you have to go basically through 2.6 times D units at station 2. And though there is no yield loss here at station 1, well, you need to do 1 unit at station 1 for every unit at station 2. And so that's also 2.6 D. But to answer the question here, for the third step here, it's basically 1.3 times the amount of demand. All right, the next question is the bottleneck. And how to find the bottleneck? Well, let's go back to the basics here and just compute the capacity level of each of the resources. Basically, we have 1 over 4, reflecting the 4-minute processing time, 1 over 4 units per minute at the first step, then a 1 over 3 at the second step, a 1 over 5 at the third step, and then a 1 over 2 at the last step. And that allows me to compute the implied utilization as the ratio of the demand rate, 2.6 D, divided by the capacity, which is 1 over 4. And that gives me here 10.4 D. In the same way, I'm going to get a 7.8 D here, right? So 2.6 D times 3, or equivalently divided by 1 over 3, 6.5 D here, and 2 D here for station number 4. And the biggest implied utilization is the bottleneck, and that is here, station number 1. Okay, so station number 1 is the bottleneck. Now, what's the process capacity? Well, the process capacity here, assuming there's enough demand, is driven by the capacity of station 1. And actually, let me take back what I just said a moment ago. Even if there's not enough demand, the process capacity is driven by the bottleneck capacity here at station 1. And so I have to figure out, well, what can this guy or girl can produce? And it's 15 units per hour, of course, right? 15 units per hour is basically 1 unit every 4 minutes. But the problem, of course, the problem is 50% of that stuff will be scrapped. And so really only 7.5 units per hour will make it to the end. Notice that the rework loop is not impacting this number because the rework does not involve the bottleneck. It really has no impact on the overall process capacity. Just one final note or observation, if you let me do this quickly, is let me quickly again comment on the rework loop. Instead of putting the capacity here as 1/5, or thus the processing time is 5 minutes, you can take also a more probabilistic approach, and I think that I did this in class earlier on. You can say that with a probability of 70%, I'm going to spend 5 minutes, and then with a probability of 30%, I'm going to spend 10 minutes, and so you get a 6.5 minutes per unit as your processing time, and that's a 1/6.5 as a capacity. And so alternatively, you can just ignore the rework loop here for the sake of demand, and just put a D here, and just ask really how many unique flow units will show up at station number 3. And then instead of then dividing by 1/5, you divide by 1/6.5, and that gives you the same 6.5 here. So you can choose either one of these approaches, whatever is easier for you. All right, the next question is about chicken eggs, and I went on Google here to inform myself about the average weight of his chicken eggs. I hope I got this right. I believe it's 47 grams, and I have this eco-friendly farmer here who is concerned about the output of well, it's not really his output, but the output of his deer chicken. And he takes a sample and finds them that they have basically a mean of 47 and a weight of 2 grams. However, you can only make money of them if they fall into the specification interval between 44 and 50. And so he wants to basically do some of the Six Sigma calculations that we talked about in class. Try it out. All right, the first one is relatively easy, I would argue, right? The first one is a capability score. And remember, this capability score looks at the upper specification limit minus a lower specification limit, which is 44, divided by 6 times the standard deviation. And so in this case here, that is simply 6 divided by 6 times 2, which is 0.5. Now that is a relatively low capability score. If you just go back through the slide that we discussed in class, you notice that you're somewhere between a 1 sigma and a 2 sigma process. And so this corresponds now to a bunch of defects. And that's what the second question is about. So what percentage of the eggs fall within the specification limits provided by the local distributor? So for that, I have to leave my PowerPoint quickly and jump into Excel. And so what I want to find out is really, I want to find out from the normal distribution, the specification limit, the upper specification limit is at 50, right? And so I have a distribution, a normal distribution with 47 mean and a 2 standard deviation. And I'm looking at the cumulative normal here. And so I have basically 93.3% of the eggs are below 50 grams. And so 1 minus that probability here gives me the probability that this egg is going to be too heavy. So 6% of the cases. As far as the probability that this egg is too light is concerned, I can again look at the normal distribution, and I can look at the scenario that I have a 44 in that normal distribution with 47 mean and 2 as a standard deviation. And that is, surprise, surprise, also 6.6%, because the mean of 47 is just right in the middle of the confidence interval. So if I add up those probabilities, since the egg can't be too heavy and too light at the same time, I'm going to get a probability of 13.36% that the egg is outside the confidence interval or the specification interval, and then 1 minus that probability equals to 86% is the probability that I had been fishing for in the question. All right, so that's that's the kind of the number 2 here. I'm just going to write CXL, and I'm going to put the Excel spreadsheet up there on the wiki. And then the third question looks at basically by how much does the standard deviation have to be improved to get to a CP score of 2/3. Okay, and so we just take the same equation as above, which was 50 minus 44 divided by 6 times, and now we leave the sigma as a variable, as an unknown to be solved for, and that we want to be equals to 2/3. And so that is equivalent to, there's basically, this is 6. 6 divided by 6 cancels out, and then we have a 1 over a sigma equals to 2/3, and that means that sigma would have to be reduced from the current state, which was 2 grams, would have to be reduced to 1.5 grams. I have to disclose here that in the questions that we're doing, we'll always assume that the current mean is actually in the middle of the specification interval. It gets a little trickier otherwise, but I'm sure you can figure it out in Excel, and I'll promise to not test you on the exam with that special nasty type of question. All right, my last question is a very creative one. It's a word matching problem in the context of the Toyota production system. And the way this works is I've provided you here with 7 descriptions of managerial practices in operations. And I have 7 Japanese terms here below. And what I want you to do is I want you to go ahead and read these statements and match them to the Japanese words. Go ahead. All right, let's tackle the first one. Let's just go A through G through each of these ones and just think about what Japanese word comes to mind. So examples of this includes workers making unnecessary movements, working on defects, idle time, all of this stuff that shouts out waste, 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 and the Japanese term for that is mura. So we have A entered here. Second, a system that enables a line worker to signal that she or he needs assistance from his supervisor, and that's used to implement the Jidoka principle. So that is the Annen chord. Now the Annen chord, this chord that goes adjacent to the line, and that helps people to alert the supervisor. And notice that at that time, the light starts blinking. It's not that all of the factory, the entire production line stops, but just a line segment, and even that is not necessarily always stopped, because typically even at Toyota, you're just going to have some buffers in there. So that's the Annen chord. C, a brainstorming technique that helps you find root causes of usually undesirable outcomes. That is a fishbone diagram, right? Also known as the Ishikawa diagram. And please don't think that Ishikawa stands for fish in Japanese, but I think that's just named by the inventor. So I really have to disclose that I speak absolutely no Japanese. I'm sorry for that. Then part D. Workers at Toyota make suggestions to process improvement. It's not just management that comes up with these suggestions, and that is the classic Kaizen process. Kaizen, the process of continuous improvement. How do you control the amount of work in process inventory? That is an easy one, especially since we're running out of options here, and that looks like Kanban. Number F, or letter F. If a plant uses this technique, the adjacent cars on the line would be mixed models. So different colors, sunroof, no sunroof, things like that. You would be producing to demand. That was a mixed model production principle that we talked about in the variety module, and that's the idea of Heijunka. And then finally, making production problems visible and stopping the production upon detection of defects. That's the logic of detect, stop, alert, and that's the idea behind Jidoka. Okay, if I'd been a little more creative, maybe these letters here, if I would read them now, would spell out something beautiful. Sorry, they are just what they are here, but that at least concludes this review session.